NVIDIA just dropped something that completely changes how AI models run at massive scale, and the infrastructure war is still figuring out what this means. We are talking about Dynamo v0.9.0, a full rebuild of the communication engine under one of the most important AI serving tools on the planet. This is the same system NVIDIA saw at GTC 2025, pushing 30 times more output per GPU while running DeepSeek R1 on Blackwell hardware. And v0.9.0 is the update that makes that foundation dramatically cleaner and more powerful. And nobody saw this particular update coming in quite this way. They ripped out two major pieces of software that the whole system used to depend on, replaced them with something smarter and lighter, added image and video model support across every backend at the same time, and sung in a preview of a brand new tool called FlashIndexer that could seriously cut down the time it takes for an AI model to respond. So let's talk about it. Here is the thing. If you're not deep in the AI infrastructure world, Dynamo might sound like just another tool, but it's actually the backbone that helps companies like Perplexity, CoreWeave, Together AI, LLaDA, and dozens of others run AI models at the largest possible scale. Jensen Huang himself called it the successor to NVIDIA's Triton inference server, which was already the standard for deploying AI models. Dynamo v0.9.0 is the version where they finished a very specific and very important rebuild they started back in v0.8.0. And when you see what they actually changed, it becomes clear this is not a small patch. This is a full engine upgrade. The first thing to understand is what they removed. Dynamo used to depend on two separate pieces of software called NATS and etcd. NATS handled the messaging layer, basically how different parts of the system talk to each other in real time. etcd handled service discovery, meaning it helped parts of the system find and register with each other. Both of these are popular tools used across the software industry, but they added extra complexity. Running them meant extra servers to manage, extra things that could break, and extra states just to get started. In v0.9.0, both of them are now completely optional and no longer required to run Dynamo. Kubernetes-native service discovery now replaces etcd. So if you're already running Kubernetes, which most production teams are, you don't need to spin up a separate etcd cluster at all. And for messaging, Dynamo built its own event planning using ZMO, which is a high-performance message transport, combined with MessagePack for fast data packing. The result is a cleaner, faster setup that reduces what people call operational dependencies. Fewer moving parts means fewer failure points and a much simpler system to manage, especially at data center scale. And honestly, the community has been asking for these for a long time. Running NATS in a production Kubernetes environment always added friction. You had to configure it, secure it, maintain it separately from everything else. Now that it's optional, teams running Dynamo in local development can get started without any of that setup. The Hello file example in the documentation was updated specifically to show this, and it was one of the first things people noticed when v0.9.0 landed. The second major story in this release is multimodal support, and this one is big. AI models are no longer just text in and text out. They handle images, video frames, audio, and mixed input all at once. And running those models at production scale requires handling a heavy step called encoding, where the image or video gets processed before the actual language model sees it. In the past, encoding and text generation had to happen on the same GPU setup. That created a bottleneck. If your image encoder is slow, your whole response is slow, even if the text generation part is fast. Dynamo v0.9.0 solves this with what they call encoder disaggregation, which basically means you can now run the encoding step on completely separate GPUs from the part that does the actual text generation. This works across all three of Dynamo's main backends, vLLM, SGLang, and TRT-LLM. For vLLM, they built something called the embedding cache connector, where the encoder stores results by a unique hash code, and the generate workers pull from that cache instead of rerunning encoding from scratch. That means if the same image shows up in multiple requests, you only encode it once. For TRT-LLM, they added a standalone encoder component that runs independently. And for SGLang, they fixed it so multimodal models can now run on a single GPU without needing a full 2 GPU setup for every single deployment. Here is the crazy part though. They also added support for diffusion-based language models. A model called LLaDA 2.0, which doesn't generate text the way a normal language model does, can now run inside Dynamo alongside regular autoregressive models in the same deployment. This is a very different kind of AI architecture, and the fact that it runs alongside standard models in one system without major re-engineering shows how fixable the new Dynamo architecture actually is. Now, let's get into how the brain of the router got smarter, because this is where vOpen 9.0 does something most frameworks haven't done yet. When you have hundreds of GPUs handling thousands of requests per second, deciding which GPU takes which request is genuinely hard. Send the wrong request to the wrong GPU and you waste compute, because the GPU has to rebuild context it already threw away. The router in Dynamo now tracks output blocks with what they call fractional decay. In plain terms, it watches how full each GPU is going to be, not just how full it is right now. And it factors in how long a response is likely to be before sending the request there. It also now accepts routing hints from the Kubernetes Gateway API Inference extension, which means external systems watching traffic patterns can give Dynamo tips about where to send things before they even arrive. Think of it like a traffic controller who gets a heads-up call before cars even enter the highway. The planner, which is the part of Dynamo that decides when to add or remove GPUs automatically, also got a serious upgrade. It now has a new option for predicting future workloads, a Kalman filter added specifically as a faster, lower latency alternative to the existing ARIMA model it already used. ARIMA is a deeper prediction tool but slower to run. The Kalman filter gives teams a way to get predictions faster when speed matters more than depth. vOpen 9.0 adds something called mooncake style warm-up, which means instead of starting cold with no idea what traffic looks like, the planner now begins with realistic data from the start, and there is a log1p fallback built in for when traffic suddenly drops to near zero, preventing the prediction model from collapsing into bad guesses. All of this feeds into SLA-driven auto-scaling, meaning the system automatically adds or removes GPUs based on whether your response time goals are being met, not just based on raw request count. Now, the preview that people in the infrastructure community flagged immediately is FlashIndexer. The full details are still limited because it's labeled a sneak preview, but the idea is clear. When you are running AI models with very long context windows, the KV cache, which is basically the model's short-term memory of a conversation, has to move between GPUs constantly. Indexing and finding the right cached data is slow. FlashIndexer is a specialized tool built specifically to make that process faster. The goal is to lower time to first token, which is the gap between when the user sends a message and when the model starts responding. That number matters enormously in real products. Every millisecond of TTFT reduction improves the user experience and allows the system to handle more traffic with the same hardware. The KV block manager also got a major technical fix that not many people noticed. Previously, when request had very long context, over 32,000 tokens, the code that stored cache events used something called recursion, where the function called itself again and again. At large enough depth, this would overflow the stack and crash. vOpen 9.0 replaced that with an iterative approach, meaning it loops instead of recurses. Stack overflow crashes on long context requests are now gone. They also added S3 compatible object storage support for KV cache transfers, meaning instead of requiring direct GPU to GPU data movement, you can now route KV cache through cloud storage backends. That opens up cheaper storage options for teams trying to reduce their infrastructure bill. Performance changes throughout the update are consistent and focused on removing hidden overhead. Multimodal requests used to go through extra steps of converting data back and forth between formats before sending it alone. That serialization and deserialization step is now gone from the main data gathering pipeline, which is directly cuts latency for image heavy requests. For TCP connections coming into the system, they rebuilt the decoder to use zero copy techniques with a bounded pool of workers, which eliminates memory leaks that used to show up under heavy load. These are exactly the kinds of fixes that don't make headlines but matter enormously when you are handling millions of requests per day. On the Kubernetes side, the operator, which is the tool that manages Dynamo deployments in a cluster, now supports rollout restarts, tolerations, and affinity rules. In simple terms, this means you can now tell Dynamo which types of GPU nodes to prefer, update a running deployment without downtime, and control where your inference workloads land in a mixed cluster. Distributed tracing now follows a request all the way from the user-facing frontend through the router and down to the inference engine, which is important for debugging production issues. And the Prometheus metric system got simplified significantly, improving 91% of unused metric score while adding support for multi-registry scrapping. For version upgrades inside vOpen 9.0, the team bumped vLLM to v0.14.1, SGLang to v0.5.8, TensorRT-LLM to v1.30 RC1, CUDA to v12.9.1 for the vLLM container, and added CUDA 13 container builds for both vLLM and SGLang. And they added CUDA 13 container builds for both vLLM and SGLang, targeting next generation GPU architectures that are already landing in production clusters. On the limitation side, to be clear, there are still real rough edges. Going to VL multimodal models don't work yet in TRT-LLM's disaggregated mode because the upstream TensorRT-LLM code hasn't added the right inference for it. There is a known issue where the planar scaling test times out because of an upstream problem in EPRF v0.4.0. Concurrent rollout restarts in Kubernetes can get stuck in a restarting state without fully completing, and some of the GAIE integration tests are failing due to image pooling errors and unrecognized CLI flags. These are all documented and actively being tracked, with several fixes already default to v1.0.0, which is targeting March 11, 2026. That's where we will wrap it up. The question now is whether the v1.0.0 release in March can hit all of those production grade targets on schedule, and whether the CUDA 13 container builds land in time for teams already deploying on next generation Blackwell hardware. Drop your thoughts below. Make sure you are subscribed, hit the like button, and I will see you in the next one.